Hello everyone, this is Atacan Okumuş and I will present you my term project DI 504 Foundations of Deep Learning course. Let's start with what is the project about. The project has targeted the digitizing in Turkish kıymetlendirme operations in a map producing process. So let's talk about what is digitizing in short terms. In map producing, after all the work finished in situ, in site, all aerial images and all data being delivered to the digitizing operators. These operators are human beings who are drawing 3D CAD maps with looking through the stereo aerial images. They detecting everything that they can do to close the semantic gap between images and the data, such as buildings in different types, mosques, rocks, trees with different kinds, rivers, abandoned places, etc. This process takes huge amounts of time and is open to mistakes because it's done by hand of a human being. In first phase of my project, I suggest the term project for DI 504 Foundations of Deep Learning course, as I would like to complete the whole classification and drawing with semantic segmentation. In fully completed project, I aim to have a CAD map from aerial images with deep learning. I think it is possible because I have the dataset in my company, over thousands of hectares of raster images and thousands of polygons. So the dataset is ready for that. For start, aim of the project is only building detection from satellite images for the term project that I am presenting right now. While I did literature review about this topic, I came across with a lot of studies, but one particular study named Deep Learning for Understanding Satellite Imagery and Experimental Survey shaped the project. So let's briefly mention what it is. This work builds on top of a released open dataset, SpaceNet version 1. We will work on SpaceNet version 2, which is in the partnership with Digital Globe, released raw multiband satellite imagery of 30 centimeter resolution for cities like Vegas, Paris, Shanghai and Khartoum, along with the corresponding annotations of buildings and roads. In this work, they focus on the problem of instance segmentation on a simplified version of the SpaceNet dataset in order to detect buildings in different urban settings on high-resolution satellite imagery. The evaluation was principally based on the intersection of union between the predicted mask and the ground truth. So from this part, I implemented that mask and the ground truth are the sets that I need to implement to my project. So mask and the ground truth. So these images are sample images from the mapping challenge dataset showing the top-down view of satellite imagery. After these inputs, we need to create masks, calculate the distance weights and give a proper size to the weights for segmentation. So this is a quick example from the paper which I implemented. I will mention about what I did for my project afterwards. So this is UNet architecture. The researchers trained UNet with ResNext 50, and we will mention about UNet in the following slides more. So then if we are done with the literature review, let's start with my project now. To initiate the project, I started with the conventional ML workflow. So ML workflow can be mentioned under 5 steps, starting with collecting the data, then prepare the data for training, then train the model and evaluate or test it, and afterwards and tune it to reach optimal solutions. So the data collection. The summary is in the screen, but to start investigating my project with ML workflow aspect, let's begin with the data collection. As I mentioned before, the literature review process helped me to pick a dataset so easily. For selecting the dataset, I implied the SpaceNet version 2 building detection challenge dataset for my work. SpaceNet, as I mentioned before, is an organization that is launched in August 2016 as an open innovation project offering a repository of freely available imagery, which is not exist in internet, with co-registered map features. And SpaceNet frequently announces challenges to develop more confident deep learning challenges about satellite imagery. So the dataset that I picked from SpaceNet version 2 has raster images and building labels, in other words, polygons. These are 3,000. There are 3,011 kilometers squares of raster data, which accompanied with over 300,000 building labels for semantic segmentation. It has 4 different cities: Vegas, Paris, Shanghai, and Khartoum, as I mentioned before. Because of the technical limitations that I had from the environment that I worked, which is Google Colab, I used a small part of the dataset for Shanghai, and we will mention these parts in the following. The pre-processing or feature extraction. For pre-processing, I didn't use any transformer to the images, as their default width and height are 650 to 650 pixels in the dataset, because it is a competition dataset and it is ready to process. Only thing that I do, because of the technical limitations of Google Colab, I use the images with the width and height of 65 to 65 pixels, which we will see in the next slides. But the actual training can be done without any pre-process of the data. For feature extraction, I applied UNet architecture, which is astonishing. Like, every time I search the implementations of this architecture from its own original paper or other developers' work, I was excited so much, because it is a very clever way to get features from images, and it is so exciting. So this is the UNet architecture. I partially mentioned a couple slides ago. I will share the Python notebook link down below for whole process, but I can partly mention how this process done in my project. I started with using double convolution for implementing the unit with kernel size of 3, stride of 1, and padding size of 1, which helps to obtain same height and width after convolutions. Because max pooling and up convolution is the point that we will change the height and width of the images. So here you can see the unit architecture that I implemented in my code. Downsampling, upsampling, pooling operations, transpose of the convolution for upsampling, how I handled with the bottleneck and the final convolution layers of the unit architecture, and how I handled the skip connections in my code, with large explanations in the code that I will share the Python notebook. As I have small amount of time here, I will process the forward function of this presentation to proceed. Like forward function. Here you can see the train and main definitions that I used in my code. Sorry about the stretching. As I mentioned before, you can find full explanations of what I have done in detail in the Python notebook that I share. But I can mention one difference and future part of the study, because it is hard to mention in the code. I use binary cross entropy with loss as loss function, due to the fact that we will have binary results in this term project, and our out channels is equal to 1 for now. But the complete whole project about digitization, it will have at least 100 class of polygons, maybe more. When that time comes, I will not use this model, obviously. I didn't decide what I should use for the next phase of the project, but for this term project, it seems enough for now. So after our training, I obtained maximum of 54% dice score in the training, and we will discuss why in next slide. So these are the hyperparameters that I used in my project, like learning rate, device is not a hyperparameter, but the batch size, number of epochs, number of workers, image height, width, and you can see the directions, directories that I used in my code, because of that I used Google Colab, and I also used the Google Drive for the dataset implementation. So as I said, these are the hyperparameters that I used in my project. I wish I could have a powerful computer to process the full dataset with full resolution of images, but I was only able to train on 300 images with batch size of 8 and resolution of 65 to 65 pixels. That's why in couple slides, like we saw, this one slide ago, we saw the evaluation result is low, I believe that whenever I have a powerful GPU that is able to process entire data with exact pixel sizes, I will be able to achieve at least 90% success rate. But 90% success rate, would it enough for winning the SpaceNet version 2 building detection challenge? No way, because they had like 99.7% of scores, like correct predictions. But this result is pretty satisfying to me as a developer that didn't have any pre-experience or of coding or mathematics like the linear algebra, and who is working in this field only for 3 to 4 months. It is really satisfying to me, and I shall take my professor and TA about that, of course. And so here is the result. The image on the top is the actual masked image from the dataset. Of course, it was not masked before. Getting the mask from TIFF and using the TIFF and the GeoJSON files to obtain the mask file was the first challenge of the study. So because of the batch size of 8, we obtained 8 images in a row in one PNG file, and image below is the guesses of my model. I think it is not bad because this is one of my first projects, but of course it is not enough for proceed for the next step. Maybe we should have a powerful GPU to train the model like in the hyperparameters that I would like, because like with there are 7,000 raster images. I was able to use only 300 of them, and with a size of 650 pixel, but I was able to use only 65 pixels for width and height. So that is why we have this bad result, I can say. I did this result comparison for 16 images only, and let's take a look. Let's take a quick look to see what happened in model. So we can see that there are resemblance in the result and the given mask data, and we can take a quick look. As I said, you can pause the video if you like. So yeah, this is not that good. As we can see from the predictions, it seems that not that successful with the hyperparameters that I forced to train the model. Only 300 images, as I said, and the pixel sizes, but it is not bad in my opinion. For conclusion, for my last words, I have to say all this deep learning journey has been quite fun and instructional to me. It doesn't matter that I didn't have code experience before. It doesn't matter that I'm not that successful in mathematics parts of it, but I became massively enthusiastic about the deep learning topic. Like no matter I receive results from the exams or homeworks, low or high, I can see that I will work on this topic in the near future of myself. But for that, I would like to thank my professor and the TA who supported me to begin this journey, and the open source data through GitHub and others. This was the presentation of building detection from satellite images for DI 504 Foundations of Deep Learning class from Atacan Okumuş. Thank you for listening.